In linear algebra, a symmetric n-real matrix M is said to be positive definite if zTMz is positive for every non-zero column vector Z of n real numbers. Here Zt denotes the transpose of Z. More generally, an n-Hermitian matrix M is said to be positive definite if zMz is real and positive for all non-zero complex vectors Z. Here Z denotes the conjugate transpose of Z. The negative definite, positive semi-definite, and negative semi-definite matrices are defined in the same way, except that the expression zTMz or zMz is required to be always negative, non-negative, and non-positive, respectively. Positive definite matrices are closely related to positive definite symmetric bilinear forms, and to inner products of vector spaces. Some authors use more general definitions of positive definite that include some non-symmetric real matrices, or non-Hermitian complex ones. Examples: the identity matrix is positive definite. Seen as a real matrix, it is symmetric, and, for any column vector Z with real entries A and B, one has. Seen as complex matrix, for any column vector Z with complex entries A and B one has. Either way, the result is positive as long as Z is not the zero vector. The real symmetric matrix is positive definite since for any non-zero column vector Z with entries A, B and C, we have. This result is a sum of squares, and therefore non-negative. And a zero only if A equals B equals C equals 0, that is, when Z is 0. The real symmetric matrix is not positive definite. If Z is the vector, one has, for any real non-singular matrix, the product is a positive definite matrix. A simple proof is that for any non-zero vector, the condition since the non-singularity of matrix means that, the examples M and N above show that a matrix in which some elements are negative may still be positive definite, and conversely a matrix whose entries are all positive may not be positive definite. Connections: the general purely quadratic real function f, z, on n real variables z1. Zn can always be written as zTMz where Z is the column vector with those variables, and M is a symmetric real matrix. Therefore, the matrix being positive definite means that F has a unique minimum when Z is 0, and is strictly positive for any other Z. More generally, a twice differentiable real function F on n real variables has an isolated local minimum at argument Z1. Zn if its gradient is 0 and its Hessian is positive definite at that point. Similar statements can be made for negative definite and semi-definite matrices. In statistics, the covariance matrix of a multivariate probability distribution is always positive semi-definite. And it is positive definite unless one variable is an exact linear combination of the others. Conversely, every positive semi-definite matrix is the covariance matrix of some multivariate distribution. Characterizations: let M be an n-Hermitian matrix. The following properties are equivalent to M being positive definite: all its eigenvalues are positive. Let Pa1dP be an eigenvalue decomposition of M, where P is a unitary complex matrix whose rows comprise an orthonormal basis of eigenvectors of M, and D is a real diagonal matrix whose main diagonal contains the corresponding eigenvalues. The matrix M may be regarded as a diagonal matrix D that has been re-expressed in coordinates of the basis P. In particular, the one-to-one change of variable y equals pz shows that zMz is real and positive for any complex vector z if and only if ydy is real and positive for any y. In other words, if D is positive definite. For a diagonal matrix, this is true only if each element of the main diagonal that is, every eigenvalue of ma is positive. Since the spectral theorem guarantees all eigenvalues of a Hermitian matrix to be real, the positivity of eigenvalues can be checked using Descartes' rule of alternating signs when the characteristic polynomial of a real, symmetric matrix M is available. The associated sesquilinear form is an inner product. The sesquilinear form defined by M is the function from Cn to C such that for all x and y in Cn, where y is the complex conjugate of y. For any complex matrix M, this form is linear in each argument separately. Therefore the form is an inner product on Cn if and only if is real and positive for all non-zero Z. That is if and only if M is positive definite. It is the Gram matrix of linearly independent vectors. Let be a list of n linearly independent vectors of some complex vector space with an inner product. It can be verified that the Gram matrix M of those vectors, defined by, is always positive definite. Conversely, if M is positive definite, it has any again decomposition par1 dp where p is unitary, d diagonal, and all diagonal elements d equals I of d are real and positive. Let E be the real diagonal matrix with entries so. Then now we let be the columns of EP. These vectors are linearly independent, and by the above M is their Gram matrix, under the standard inner product of Cn, namely, its leading principal minors are all positive. The kth leading principal minor of a matrix M is the determinant of its upper left K by K submatrix. It turns out that a matrix is positive definite if and only if all these determinants are positive. This condition is known as Sylvester's criterion, and provides an efficient test of positive definiteness of a symmetric real matrix. Namely, the matrix is reduced to an upper triangular matrix by using elementary row operations, as in the first part of the Gaussian elimination method, taking care to preserve the sign of its determinant during pivoting process. Since the kth leading principal minor of a triangular matrix is the product of its diagonal elements up to row k, Sylvester's criterion is equivalent to checking whether its diagonal elements are all positive. This condition can be checked each time a new row k of the triangular matrix is obtained. It is a unique Kilsky decomposition. The matrix M is positive definite if and only if there exists a unique lower triangular matrix L, with real and strictly positive diagonal elements, such that M equals LL. This factorization is called the Kilsky decomposition of M, quadratic forms. The quadratic form associated with a real matrix M is the function QARN such that Q, x, equals xTMx for all x. It turns out that the matrix M is positive definite if and only if it is symmetric and its quadratic form is a strictly convex function. More generally, any quadratic function from Rn to A can be written as xTmx plus xtb plus c where M is a symmetric NA, N matrix, B is a real N vector, and C a real constant. This quadratic function is strictly convex when M is positive definite, and hence has a unique finite global minimum, if and only if M is positive definite. For this reason, positive definite matrices play an important role in optimization problems. Simultaneous diagonalization, asymmetric, and a symmetric and positive definite matrix can be simultaneously diagonalized, although not necessarily via a similarity transformation. This result does not extend to the case of three or more matrices. In this section we write for the real case. Extension to the complex case is immediate. Let M be a symmetric and N asymmetric and positive definite matrix. Write the generalized eigenvalue equation as equals 0 where we impose that x be normalized, that is, xTnx equals 1. Now we use Kilsky decomposition to write the inverse of n as qtq. Multiplying by q and qt, we get q, ma in, qtx equals 0, which can be rewritten as equals iy where yty equals 1. Manipulation now yields mx equals nxi where x is a matrix having as columns the generalized eigenvectors and I is a diagonal matrix with the generalized eigenvalues. Now pre-multiplication with xt gives the final result, xtmx equals I and xtnx equals I, but note that this is no longer an orthogonal diagonalization. Note that this result does not contradict what is said on simultaneous diagonalization in the article diagonalizable matrix, which refers to simultaneous diagonalization by a similarity transformation. Our result here is more akin to a simultaneous diagonalization of two quadratic forms, and is useful for optimization of one form under conditions on the other. For this result see Horn and Johnson, 1985, page 218 and following. Negative definite, semi-definite and indefinite matrices. A Hermitian matrix is negative definite, negative semi-definite, or positive semi-definite if and only if all of its eigenvalues are negative, non-positive, or non-negative, respectively. Negative definite, the n-Hermitian matrix M is said to be negative definite if for all non-zero x and Cn, where x is the conjugate transpose of x. A matrix is negative definite if its kth order leading principal minor is negative when k is odd, and positive when k is even. Positive semi-definite, M is called positive semi-definite if for all x in Cn. A matrix M is positive semi-definite if and only if it arises as the Gram matrix of some set of vectors. In contrast to the positive definite case, these vectors need not be linearly independent. For any matrix A, the matrix AA is positive semi-definite, and rank A equals rank AA. Conversely, any Hermitian positive definite matrix M can be written as MA equals LL. This is the Kolsky decomposition. A Hermitian matrix is positive semi-definite if and only if all of its principal minors are non-negative. It is however not enough to consider the leading principal minors only, as is checked on the diagonal matrix with entries 0 and -1. Negative semi-definite, it is called negative semi-definite if for all x in Cn. Indefinite a Hermitian matrix which is neither positive definite, negative definite, positive semi-definite, nor negative semi-definite is called indefinite. Indefinite matrices are also characterized by having both positive and negative eigenvalues. Further properties: if M is an Hermitian positive semi-definite matrix, one sometimes writes Ma A permil beta 0, and if M is positive definite one writes Ma A 0. The notion comes from functional analysis where positive semi-definite matrices define positive operators. For arbitrary square matrices M, N we write Ma A permil beta N if Ma A and Na A permil beta 0. That is, Ma A N is positive semi-definite. This defines a partial ordering on the set of all square matrices. One can similarly define a strict partial ordering Ma N. Every positive definite matrix is invertible and its inverse is also positive definite. If Ma A permil beta Na A 0 then Na 1 AA permil beta Ma 1 AA 0, and a Shan AA 0. Moreover, by the min-max theorem, the kth largest eigenvalue of M is greater than the kth largest eigenvalue of N. If M is positive definite and Ra A0 is a real number, then Rm is positive definite. If M and N are positive definite, then the sum Ma plus N and the products MNM and NMN are also positive definite. If MN equals ANM, then MN is also positive definite. Every principal submatrix of a positive definite matrix is positive definite. QTMQ is non-negative definite. If Q is invertible, then Q1MQ and QTMQ are positive definite. The determinant of M is bounded by the product of its diagonal elements. The diagonal entries MI are real and non-negative. As a consequence the trace, TR, M, AA permil beta 0. Furthermore, since every principal submatrix is positive definite, and thus a matrix M is positive semi-definite if and only if there is a positive semi-definite matrix B with B2 and equals M. This matrix B is unique, is called the square root of M, and is denoted with bar equals M1/2. If Ma and Na A0 then M12 AA0. If M is a symmetric matrix of the form Ij equals M, E at J, and the strict inequality holds, then M is strictly positive definite. Let Ma A0 and N Hermitian. If Ma plus and Ma permil beta 0 then Na permil beta 0. If Ma A0 is real, then there is AIAA0 such that Ma AII, whereas the identity matrix. If MK denotes the leading K by K minor, is the kth pivot during LU decomposition. The set of positive semi-definite symmetric matrices is convex. That is, if M and N are positive semi-definite, then for any I plus or minus between 0 and 1, I plus or minus M plus N is also positive semi-definite. For any vector X. This property guarantees that semi-definite programming problems converge to a globally optimal solution. If M, now a permil beta 0, although Mn is not necessarily positive semi-definite, the Kronecker product Ma-Ash, and per-mil beta 0, the Hadamard product Ma-A, and per-mil beta 0, and the Frobenius product Ma and per-mil beta 0. Regarding the Hadamard product of two positive semi-definite matrices Ma equals a, Mij, AA per-mil beta 0, Na per-mil beta 0, there are two notable inequalities: Oppenheim's inequality, det, Ma A, and N, A per-mil N det, M, det, N. Block matrices, A positive 2NA, 2N matrix may also be defined by blocks, where each block is NA, N. By applying the positivity condition, it immediately follows that A and E are Hermitian, and C equals B. We have that zMz are per-mil 0 yen for all complex Z, and in particular for Z equals T. Then, a similar argument can be applied to D, and thus we conclude that both A and E must be positive definite matrices, as well. Converse results can be proved with stronger conditions on the blocks, for instance using the Scher complement. On the definition, consistency between real and complex definitions, since every real matrix is also a complex matrix, the definitions of positive definite for the two classes must agree. For complex matrices, the most common definition says that M is positive definite if and only if zMz is real and positive for all non-zero complex column vectors Z. This condition implies that M is Hermitian, that is, its transpose is equal to its conjugate. To see this, consider the matrices A equals /2 and B equals /2I, so that M equals A plus IB and zMz equals ZRs plus SBZ. The matrices A and B are Hermitian, therefore ZRs and ZBZ are individually real. If zMz is real, then ZBZ must be 0 for all Z. Then B is the zero matrix and M equals A, proving that M is Hermitian. By this definition, a positive definite real matrix M is Hermitian, hence symmetric. And zTMz is positive for all non-zero real column vectors Z. However, the last condition alone is not sufficient for M to be positive definite. For example, if then for any real vector Z with entries A and B we have zTMz equals A plus B equals A2 plus B2, which is always positive if Z is not 0. However, if Z is the complex vector with entries 1 and I, one gets zMz equals 1, AI, M, 1, I, T equals 1 plus I, 1 AI, 1, I, T equals 2 plus 2I, which is not real. Therefore, M is not positive definite. On the other hand, for a symmetric real matrix M, the condition zTMz greater than 0 for all non-zero real vectors Z does imply that M is positive definite in the complex sense. Extension for non-symmetric matrices. Some authors choose to say that a complex matrix M is positive definite if Re, zMz, 0 for all non-zero complex vectors Z, where Re, C, denotes the real part of a complex number C. This weaker definition encompasses some non-Hermitian complex matrices, including some non-symmetric real ones, such as. Indeed, with this definition, a real matrix is positive definite if and only if zTMz greater than 0 for all non-zero real vectors Z, even if M is not symmetric. In general, we have Re, zMz, 0 for all complex non-zero vectors Z if and only if the Hermitian part /2 of M is positive definite in the narrower sense. Similarly, we have xTMx greater than 0 for all real non-zero vectors X if and only if the symmetric part /2 of M is positive definite in the narrower sense. In summary, the distinguishing feature between the real and complex case is that a bounded positive operator on a complex Hilbert space is necessarily Hermitian, or self-adjoint. The general claim can be argued using the polarization identity. That is no longer true in the real case. See also, Kolsky decomposition, covariance matrix, M matrix, positive definite function, positive definite kernel, Scher complement, square root of a matrix, Sylvester's criterion, notes. References: Horn, Roger A. Johnson, Charles R., Matrix Analysis, Cambridge University Press. ISBN A978-0-521-38632-6A. Rajendra Basia. Positive definite matrices. Princeton Series in Applied Mathematics, 2007. ISBN 978-0-691-12918-1. External links: Haswinkel, Mikhail, ed., Positive Definite Form, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-Fora, Wolfram Math World, Positive Definite Matrix.